Hi, I'm Paula Endrös, and I'm in my first year of PhD at the Norwegian University of Science and Technology with the supervision of Nima, Razavi, Johnsen, and Shulu. And today I'm going to present the hydrating behavior in titanium 6-4 alloy manufactured with electron beam powder bed fusion. So this is the structure of the presentation. Since 15 minutes is not so much time, I'm going to be short on the introduction and keep it to the scope of the presentation. Then I'm going to give some the most relevant microstructural features relevant to hydrogen embrittlement about this material without hydrogen first. Then I'm going to explain the hydrating behavior observed on the samples, and finally some concluding remarks. So, first, why we do a distinction about additive manufacturing. So it's a rapid increasing technology that is also expected to increase a lot in the future, which started previously with manufacturing prototypes, but now it's already manufacturing final parts that can be directly implemented into final applications. And it has many advantages, which I'm sure that you almost have heard of them. Nevertheless, in regard to hydrogen embrittlement, it adds another complexity factor, since hydrogen can interact differently with these different microstructural features that are highly dependent on the manufacturing route, on the additive manufacturing technique, since it gives these complex thermal cycles that leads to different microstructural features. And therefore, even though this alloy has been previously studied for conventional alloys, the knowledge cannot be directly applied into additive manufactured one. And in metals, there are mainly two groups of additive manufacturing techniques, and I'm focusing on the powder bed fusion type. And in this case, instead of laser, electron beam is used as the energy source to selectively melt the powder in the bed. And as previously mentioned, the higher cooling rates associated to the additive manufacturing processes lead to many different microstructures, and the main differences are in the grain refinement and also in the different microstructures, which leads to differences in the mechanical performance as well as in the corrosion resistance, hence hydrogen embrittlement. And when also studying titanium alloys, there made a distinction between alpha titanium, alpha beta titanium, and beta titanium alloys. And titanium 6-4 is very representatively used for dual phase alloys. And it's also a good choice for studying additive manufacturing applications, since it's intended for high-end applications where also applying additive manufacturing would make sense. So to start with, as mentioned, it's a dual phase microstructure, which is fully lamellar as shown in the SEM image. It's backscattered. And you can see that the gray darker phase is the alpha phase, and the white phase is the beta phase. And we can also see that the grain size is significantly lower compared to conventional alloys, which also leads to higher grain boundaries density that also is going to have an effect on the hydrogen embrittlement. And in this case, the beta phase, it's 8.85% in average. And this is important because, well, here again, the dual phase is observed with X-ray diffraction, and you can see the black peaks are alpha phase and the green peaks are beta phase. And this is important to mention because alpha has an HCP structure, whereas beta has a BCC structure. And due to this difference in structure, the hydrogen has a different solubility and diffusivity in both phases. And this is higher in the beta phase. So the content of the beta phase makes a difference in the susceptibility to hydrogen embrittlement in this alloy. So now coming already to charging the samples, throughout the presentations, the samples were galvanostatically charged in phosphoric acid and glycerin in 1:2 proportion, and the time was always kept constant, and the content of hydrogen was increased by increasing the current density. And to find the threshold where the hydride started forming, we saw that at minus 0.3, the hydrogen is still in solid solution, and by increasing it to 0.5 milliampere per square centimeters, we can observe the hydride formation due to this appearance of the peaks. And here it's interesting to see that the two hydrides were formed, both with the FCC microstructure. Nevertheless, it was reported that for additively manufactured titanium alloy, that these two hydrides were not previously, they were recently reported for the first time, and they have different lattice parameters compared to the delta hydrides that were observed in conventional alloys. And when performing a high temperature XRD, we can also see the decomposition of the hydrides, and we can see that the peaks, they disappear above 265 degrees, whereas there's the decomposition of the hydrides. And here it's also interesting to notice that in literature, it's reported that the delta hydrides, they decompose at higher temperatures, around 400 or 450 degrees. And having a lower decomposition temperature can mean that the bonding strength of this hydride is weaker than the reported for conventional alloys. And when analyzing the diffusion of the hydrogen inside the metal, we can see that the beta content as well as the size and distribution can have an impact on the hydrogen behavior. And here on this side, it's the surface, and we can see there's this region of coarser grains where no hydrides are formed. Yeah, well, the hydrides are the darkest phase that forms between the alpha and the beta grains due to this change in solubility. And we can see that, here a bigger image, that even though it's close to the surface, there was no saturation reached, whereas with decreasing the grain size and having less continuous beta phase, that a higher quantity of hydrides were formed, which is different to what would be expected, because in a conventional titanium alloy or selectively laser melted alloy, there was normally like a gradient of hydrides formation, and it didn't reach the bulk. But in this case, the hydrides, they reach until the bulk of the sample, which is associated to this continuous beta phase and content. And when seeing the embrittlement effect of this hydride condition, we performed tensile testing, and with a 10⁻⁴ strain rate, and we see a clear embrittlement effect due to the hydride condition, and that there was a 17.4% reduction in the ultimate tensile strength, as well as a 44.5% reduction in the elongation at break. And when taking a look at the fractography images, we can see that, the uncharged sample, we can see mostly like these locations and ductile features. Here's a small defect that became a little bit bigger after the tensile test. And then when charging with hydrides, we see here that some micro cracks are formed close to the surface, as well as bigger cracks. And also these micro cracks that indicate the embrittlement. And when taking a look at the fracture surface, we can see that dimple morphology, which indicates the ductility of the break. And there was some melt effect, but even though there was this melt effect, the area around was ductile with dimples. And here, more interestingly, we see that when charging with hydrogen, that there appear fragile features as well as micro cracks. And yeah, also close to the defect, we see this fragile region that is also associated with a higher content of hydrides. And we wanted to see that if the microcracks, if they were formed because of defects during the manufacturing of the sample, or if it could be associated to the formation of the hydrides. And this is the surface that was polished parallel to the fracture surface. And we can see that for the uncharted samples, no microcracks are observed. Nevertheless, I'm not sure if it's visible, but there are these a considerable amount of microcracks that here, the higher magnification, we can see that they propagate along the alpha beta phase boundaries. And yeah, so we can say that the hydrides influence this cracking. So overall, as a conclusion, we can see that in this material, as expected, hydrides are formed. They have an FCC microstructure, but they decompose at a lower temperature than expected. They form at the alpha beta phase boundaries due to the change in solubility between the both phases. An increase in the connectivity and the content of the beta increases acts like fast diffusion paths for the hydrogen to reach deeper into the bulk. And this also causes that the hydrides can reach also deeper into the bulk. And finally, at this scale of testing, because the samples, they were pretty small, we can say that the lamellar microstructure and the distribution of the beta contributes more to the hydrogen embrittlement than maybe the porosity or manufacturing related defects that can be found in the sample. And this is mostly associated to the hydride formation. So thank you very much.